On May 23, 1944, a small aircraft rolled onto the grass at RAF Harwell in Oxfordshire. It had been trucked in pieces from a tiny workshop in Buckinghamshire that morning, disassembled in approximately 1 hour, transported by road, and reassembled in just over an hour at the airfield. The man who designed it had never built more than 4 aircraft in his entire career. He had no government contracts for mass production. He had no political connections in Whitehall. What he had was a vision for the perfect fighter plane, a vision born from tragedy and refined through obsessive attention to every detail. 7 miles away in Whitehall, Air Ministry officials were already drafting memoranda that would seal the aircraft's fate before it ever proved what it could do. They had decided the future belonged to jet propulsion. Piston engines were yesterday's technology. Any aircraft powered by a propeller, no matter how advanced, no matter how carefully engineered, was obsolete before it left the ground. The designer's name was James Martin. His aircraft was the MB.5, and the officials who dismissed it were about to make one of the most consequential misjudgments in British aviation history. The story of how Britain cancelled its most advanced piston fighters is not simply a tale of technological transition. It is a story about how institutions make decisions under pressure, how assumptions harden into policy before evidence can challenge them, and how the future rarely arrives as neatly as planners expect. The men who chose to abandon propeller-driven aircraft believed they were racing toward tomorrow. They did not anticipate that tomorrow would still need yesterday's machines. The roots of the MB.5 stretched back to tragedy. On September 12, 1942, Captain Valentine Baker took off from RAF Wing in Buckinghamshire at the controls of the MB.3, the predecessor to what would become the MB.5. Baker was not just a test pilot. He was James Martin's business partner, his closest friend, and the human being who translated Martin's engineering genius into controlled flight. The MB.3 was powered by a Napier Sabre engine, a complex and temperamental 24-cylinder H-configuration power plant that produced enormous power but suffered from chronic reliability problems. The Sabre had plagued the Hawker Typhoon program with failures and fires. It demanded careful handling and meticulous maintenance. On that September morning, somewhere over the Buckinghamshire countryside, a sleeve drive crank inside the Sabre shattered. The engine seized instantly, without warning, leaving Baker with a dead propeller and a gliding aircraft searching desperately for somewhere to land. He almost made it. Baker spotted a field below and set up for a forced landing. The MB.3 touched down successfully, but its momentum carried it across the field toward the boundary. The aircraft struck a hayrick at the edge of the field. The impact ruptured the fuel tanks. Aviation fuel sprayed across the hot engine. The aircraft burst into flames. Valentine Baker, aged 34, a man who had devoted his life to advancing British aviation, died in the wreckage of his best friend's creation. The loss devastated James Martin. Born on September 11, 1893, in Crossgar, County Down, in what was then Ireland, Martin was a self-educated engineer who had left school at 14 and taught himself aeronautical design through relentless study and experimentation. He had built his first aircraft in 1929 and founded his company with Valentine Baker shortly afterward. They had designed aircraft together, tested aircraft together, dreamed together of building the finest fighter in the world. Now Baker was gone, and Martin was alone with his drawings and his grief. Many men would have abandoned aviation after such a loss. James Martin did the opposite. He threw himself into designing a new aircraft that would honour his friend's memory. An aircraft so carefully engineered that nothing would fail, nothing would surprise, nothing would kill the pilot who trusted it with his life. But he also began working on something else, something that consumed increasing amounts of his attention in the years that followed. He became obsessed with finding ways to help pilots escape from stricken aircraft before those aircraft killed them. The ejection seat program that would eventually make Martin-Baker the most important name in aviation safety, that would save thousands of lives across decades of service, grew directly from the ashes of Valentine Baker's death. Martin abandoned his planned MB.4 redesign in early 1943, judging it too compromised by the MB.3's basic architecture. He started fresh, incorporating every lesson learned from the earlier aircraft and every insight gained from studying the successes and failures of fighters across the world. The resulting MB.5 was built to Air Ministry Specification F, 1839. but it reflected Martin's personal vision far more than any government requirement. The aircraft was built around a Rolls-Royce Griffon 83 engine, producing 2,340 horsepower at maximum power with a two-stage, two-speed supercharger. This drove a six-blade contra-rotating propeller that eliminated the torque effects which plagued single propeller installations. The engine installation was designed for rapid removal and replacement. The entire power plant could be changed in the field by a trained crew in a fraction of the time required for contemporary fighters. The fuselage was constructed from a tubular steel frame with bolted joints, covered by aluminium skin panels, attached with Zu's quick-release fasteners fitted with rubber seals. Large, detachable panels gave mechanics unprecedented access to every system. A fitter could reach any component without contorting himself into impossible positions or removing dozens of screws. The instrument panel sat on a subframe that hinged open like a door, revealing the entire electrical system behind it. All control systems, including brakes, split flaps, and undercarriage, ran on 350 pounds per square inch pneumatics, eliminating the complexity and maintenance burden of hydraulic systems entirely. Martin designed the cockpit with obsessive attention to the pilot's needs. Every control fell naturally to hand. Every instrument sat in logical relationship to every other. The canopy provided exceptional visibility. The seat was comfortable for long missions. Even the emergency systems were designed for rapid use under stress. The official performance figures were impressive by any standard. 460 miles per hour at 20,000 feet, an initial climb rate of 3,800 feet per minute, a service ceiling of 40,000 feet, a range of approximately 1,100 miles on internal fuel. The aircraft carried four 20mm Hispano cannons with 200 rounds per gun, giving it formidable firepower for air-to-air combat or ground attack. But the numbers told only part of the story. What made the MB-5 remarkable was how it flew, how it felt in a pilot's hands, how it responded to control inputs with precision and predictability. The first flight did not go well. Captain Brian Greenstead, a Rotol test pilot who had been seconded to Martin-Baker after Valentine Baker's death, took the MB-5 into the air at Harwell and immediately encountered serious problems. The aircraft was directionally unstable, yawing unpredictably in a way that made precise control difficult and combat maneuvering potentially dangerous. Greenstead landed after a short flight and delivered a blunt assessment to James Martin. He called the MB-5 an absolute swine to fly. Martin diagnosed the problem immediately. The contra-rotating propellers produced more blade area and different airflow characteristics than the single propeller of the MB-3. The torque was eliminated, but the slipstream effect on the tail was intensified. The vertical stabilizer and rudder, essentially unchanged from the earlier design, were simply too small to cope with the increased aerodynamic forces acting on the tail. Over the following 6 months, Martin designed and fitted a significantly larger vertical tail assembly. The modification required careful wind tunnel testing and flight verification. Martin would accept nothing less than perfection. The transformation was dramatic. When Greenstead flew the modified aircraft in late 1944, he reversed his assessment completely. He now called the MB-5 a super ship to fly, one that earned the respect of everyone associated with it. But those months of modification work proved fatal to the program's chances. By the time the MB-5 was ready to demonstrate its true capabilities, the war in Europe was clearly approaching its end. The Normandy invasion had succeeded. Allied armies were pushing into Germany. The Luftwaffe was being systematically destroyed. The Air Ministry had already made its fundamental decision about the future. Jets were coming. Resources would be concentrated on the Gloster Meteor and the de Havilland Vampire. There was no room in the budget, no space in the planning documents, no political will for another piston fighter, no matter how good it might be. The formal cancellation came in October 1944, when James Martin was informed by Air Ministry officials that the MB-5 would not enter production because its service entry would take too long. At that point, the aircraft had accumulated only approximately 40 flight hours. It was still resolving the stability problems that the larger tail had addressed. The decision-makers were judging the MB-5 at its worst moment, not waiting to see what it could become at its best. They never gave it a fair chance to prove what it could do. One dramatic incident nearly ended the MB-5's story prematurely. In late October 1945, the aircraft was demonstrated before distinguished visitors at the exhibition of German aircraft and equipment at RAF Farnborough. Winston Churchill, the former wartime Prime Minister who was now leader of the opposition, was among those present to witness what British engineering had achieved. Brian Greenstead took the MB.5 aloft and put it through its paces, demonstrating the handling qualities and performance that had impressed every pilot who flew it. Then disaster struck. The Griffon engine catastrophically failed in flight. A piston shattered inside the engine block. Greenstead's cockpit filled with smoke and oil as the power plant tore itself apart. He had seconds to decide what to do, whether to abandon the aircraft over the crowd below or attempt a dead-stick landing with virtually no visibility. Greenstead chose to stay with the aircraft. While jettisoning the canopy at over 400 miles per hour to clear the smoke, his arm was caught in the slipstream and severely dislocated. The canopy itself struck the tailplane, damaging the aircraft's control surfaces. Despite the injury, despite the smoke, despite flying an aircraft with a seized engine and damaged tail, Greenstead executed a successful forced landing on the airfield. He walked away from the aircraft, his arm hanging useless at his side, having demonstrated courage that matched the engineering excellence of the machine he had just saved. The incident could have been a turning point. Here was dramatic proof that the MB.5 could survive catastrophic failure, that its pilot could bring it home when everything went wrong. But by October 1945, the decision had already been made. The demonstration impressed the spectators but changed nothing in the planning documents. The MB.5 remained cancelled. The irony was bitter. The jets meant to replace piston fighters were not yet capable of replacing them in any meaningful sense. The Gloster Meteor F-1, which entered RAF service on July 12, 1944, when the first aircraft arrived at No. 616 Squadron at RAF Culmhead in Somerset, had a maximum speed of approximately 415 miles per hour at low altitude. This was no faster than the Hawker Tempest 5 or the latest Griffon-powered Spitfire Mark 14. The Meteor's jet engines gave it potential for development, but in 1944 that potential remained largely unrealized. The Meteor's first operational missions, flown on July 27, 1944, were anti-V-1 flying bomb patrols over Kent. The pilotless V-1 cruise missiles approached Britain at speeds around 400 miles per hour, making them difficult targets for conventional fighters. The Meteor was deployed because its speed, marginally higher than the V-1's, gave pilots a better chance of intercept. The results were modest. The Meteor eventually scored 14 confirmed V-1 kills during the entire campaign. One of these kills came on August 4, 1944, and entered aviation legend. Flying Officer T.D. Dean, known throughout the RAF as Dixie, was pursuing a V-1 over Kent when his four 20mm cannons jammed. The flying bomb droned on toward London, carrying its 1-ton warhead toward civilian targets. Rather than break off the intercept and let the bomb escape, Dean maneuvered his Meteor alongside the V-1 and slid his wingtip beneath its wing. Using the aerodynamic disruption, he tipped the flying bomb off balance, sending it tumbling out of control to crash harmlessly in the Kent countryside. The Imperial War Museums still hold the actual wingtip from Dean's aircraft, inscribed with the date of the engagement. The Meteor was deliberately kept from flying over enemy territory throughout the remainder of the war. RAF commanders feared that a Meteor might be shot down or suffer mechanical failure over German-held territory, allowing the enemy to capture the aircraft and reverse engineer its technology. The jet fighter that was supposed to represent the future of air warfare spent the war chasing unmanned missiles and staying carefully on the British side of the Channel. It never engaged an enemy fighter in combat during the Second World War. The de Havilland Vampire, which had first flown on September 20, 1943, with Geoffrey de Havilland Jr. at the controls at Hatfield Aerodrome, was faster than the Meteor at approximately 540 miles per hour. But it did not enter RAF squadron service until 1946, well after the war had ended. The jet age that Air Ministry planners were so eager to embrace existed more in imagination and planning documents than in operational reality during the critical years of 1944 and 1945. The transformation came later, when improved engines and refined designs delivered on the jet's promise. On November 7, 1945, Group Captain Hugh Wilson set the first official jet air speed record at 606 miles per hour in a specially modified Meteor. On September 7, 1946, Group Captain Edward Donaldson pushed the record to 616 miles per hour. By then, the Meteor F4, with its more powerful Derwent 5 engines producing 3,500 pounds of thrust, was delivering 585 miles per hour in level flight, genuinely faster than any piston fighter could ever achieve. But that was 1946 and beyond. The decisions that killed the MB.5 were made in 1944 and 1945, when the jets that supposedly made piston fighters obsolete were actually slower than the piston fighters they were meant to replace. James Martin was not the only British designer whose work was sacrificed on the altar of jet-age enthusiasm. At Supermarine's works in Southampton, chief designer Joseph Smith was pursuing a parallel path toward the same dead end. Smith had inherited leadership of Supermarine's design team under tragic circumstances. Reginald Mitchell, the genius who created the Spitfire, died of rectal cancer on June 11, 1937, at the age of 42. Mitchell had seen his creation fly, but did not live to see it win the Battle of Britain or become the most famous fighter aircraft in history. Joseph Smith, who had served as Mitchell's chief draftsman, stepped into the role of chief designer and devoted himself to improving, refining, and eventually replacing his predecessor's masterwork. By 1942, Smith and his aerodynamics team at Supermarine, working with researchers at the National Physical Laboratory at Teddington, recognized that the Spitfire's iconic elliptical wing was becoming a liability at high speeds. As aircraft dove faster and faster, they encountered compressibility effects that could cause loss of control. The Spitfire's wing structure, despite its beautiful elliptical planform, flexed under aerodynamic loads in ways that limited safe diving speed to approximately 480 miles per hour. Any attempt to exceed this limit risked structural failure or loss of aileron effectiveness. The solution was a completely new wing design using laminar flow aerodynamics. Laminar flow theory predicted that a carefully shaped wing with very smooth surfaces could maintain attached airflow to a much higher percentage of chord length, reducing drag significantly and raising the critical Mach number at which compressibility effects began. American researchers had pioneered the concept, and British engineers were eager to apply it. Supermarine issued Internal Specification number 470 on November 30, 1942, outlining the design requirements for a new wing. The document called for a wing that would raise the critical Mach number, achieve a faster rate of roll than any existing fighter, and reduce profile drag compared to the Spitfire's elliptical wing. The result would be smaller than the Spitfire wing, with 210 square feet of area compared to the Spitfire's 242 square feet, and 200 pounds lighter. The familiar elliptical planform would give way to straight-tapered leading and trailing edges that were easier to manufacture and better suited to laminar flow characteristics. The Air Ministry issued Official Specification F-143 in February 1943, formalizing the requirement. After considerable debate about names, with suggestions including Victor and Valiant receiving consideration, the new aircraft was christened Spiteful in March 1944. Winston Churchill himself took an interest in the naming process. The Spiteful was not merely an improved Spitfire, it was a substantially new aircraft that happened to share some components with its famous predecessor. The undercarriage retracted inward rather than outward, giving a wider track that addressed one of the Spitfire's most persistent ground handling complaints. The tail surfaces were redesigned. The cockpit was raised to improve visibility. Only the basic fuselage structure and some systems components carried over from the Spitfire. Geoffrey Quill, Supermarine's chief test pilot, and the second man ever to fly a Spitfire back in March 1936, made the first flight of the Spiteful prototype on June 13, 1944. At RAF High Post in Wiltshire, the aircraft, serial number N660, was technically a hybrid, using a modified Spitfire Mark 14 fuselage mated to the new laminar flow wing. Quill found the aircraft comfortably faster than a standard Spitfire Mark 14, but he also discovered troubling characteristics that would plague the program throughout its existence. The new laminar flow wing had fundamentally different stalling behavior than the Spitfire's elliptical wing. On the Spitfire, the inner wing root stalled first, giving the pilot ample warning through buffeting, while the outer wing with its ailerons remained effective for control. This benign stall characteristic was one of the Spitfire's greatest virtues, making it forgiving and safe even for inexperienced pilots. On the Spiteful, the outer wing with its ailerons stalled first, exactly opposite to what a pilot wanted. This meant that at high angles of attack, just when a pilot most needed aileron control, the ailerons became ineffective first. The aircraft could flick into a spin with little warning. Worse was to come. On September 13, 1944, prototype NN660 was engaged in a low-altitude mock combat exercise with a standard Spitfire Mark 14. Test pilot Frank Furlong was at the controls, ringing out the Spiteful in simulated combat maneuvering. Without warning, the aircraft departed controlled flight and crashed. Furlong was killed instantly. He was one of Supermarine's most experienced test pilots, a man who had flown countless hours in Spitfires and their derivatives. No definitive cause was ever established, but the accident investigation raised the possibility that aileron control rods had momentarily jammed or disconnected during high-G maneuvering, a possibility that Jeffrey Quill himself had experienced in a later flight when he felt the ailerons momentarily freeze during a hard turn. The Spiteful program continued despite the tragedy. Engineers enlarged the vertical stabilizer area by 28% and the horizontal stabilizer area by 27% to address directional stability problems. The second prototype first flew on January 8, 1945, with a redesigned fuselage featuring a raised cockpit and bubble canopy that gave the pilot much better visibility than the original Spitfire-style canopy. The performance figures achieved were genuinely impressive. The Spiteful F-14 achieved 483 miles per hour at 21,000 feet, with its Griffon 69 engine producing 2,375 horsepower. An experimental F-16 variant, fitted with a Griffon 101 engine featuring a unique two-stage 3-speed supercharger, reached 494 miles per hour at 27,800 feet in 1947. This was the fastest speed ever recorded by a British piston-powered aircraft in level flight, a record that stands to this day because no British piston fighter has flown since. But the Air Ministry's evaluators at the Aeroplane and Armament Experimental Establishment at Boscombe Down rated the Spiteful below average overall. They criticised poor cockpit layout compared to contemporary fighters. They noted excessive time required to refuel and rearm the aircraft, a critical consideration for operational squadrons. They complained about poor build quality in the production specimens. The laminar flow wing that was the aircraft's entire reason for existence proved problematic in service conditions. Any contamination on the wing's leading edge, whether bugs, mud, raindrops, or even frost, destroyed the laminar flow and significantly reduced the speed advantage the wing was supposed to provide. The production order told the story of the Spiteful's decline in stark numbers. The Air Ministry initially ordered 650 aircraft, anticipating that the Spiteful would replace the Spitfire in frontline service. This was progressively cut as priorities shifted, first to 390, then to 80, then to just 22, by May 1946. The final order, placed on December 16, 1946, was for just 16 aircraft, essentially only those airframes already built or nearly complete on the production line. In the end, 19 Spiteful aircraft were completed, 2 prototypes plus 17 production machines. None entered operational squadron service. Most were sold for scrap in July 1948. Not a single surviving example exists today. The naval variant, called the Seafang, fared no better. Developed for the Fleet Air Arm as a carrier-based fighter, the Seafang existed in 2 marks. The F-31 was essentially a Spiteful, with an arrestor hook added. The definitive F-32 featured hydraulically folding wings for carrier stowage and contra-rotating propellers to eliminate torque on takeoff and landing. Test pilot Mike Lithgow conducted deck landing trials on HMS Illustrious on May 21, 1947, completing 8 successful landings. But the program was cancelled shortly afterward, when the Seafang's performance advantage over the existing Seafire Mark 47 was judged insufficient to justify disrupting jet fighter production. Of 150 Seafangs ordered in May 1945, only approximately 18 were built across all variants. The Spiteful's most enduring contribution was paradoxically its wing. In late 1943, Joseph Smith had proposed mounting the laminar flow wing on a new fuselage housing a Rolls-Royce Neanjet engine. This concept evolved through several iterations into the Supermarine Attacker, which entered Fleet Air Arms service in August 1951 as the Royal Navy's first operational jet fighter. The design lineage continued through the Type 510 swept-wing experimental aircraft to the Supermarine Swift, giving the Spiteful's wing an afterlife its fuselage was denied. The decisions that cancelled these advanced piston fighters were made by experienced professionals who genuinely believed they were steering Britain toward the future. Understanding their reasoning requires examining who they were and what pressures they faced. Sir Wilfrid Freeman served as chief executive of the Ministry of Aircraft Production from October 1942 until 1945. He was arguably the most influential single figure in RAF aircraft selection during the war, the man who championed the Hurricane, Spitfire, Mosquito, Lancaster, and Merlin-engined Mustang when others doubted them. Freeman's nickname for the de Havilland Mosquito, Freeman's Folly, became an ironic badge of honor when that wooden wonder proved one of the most versatile aircraft of the war. Critically for jet development, in December 1942, Freeman authorized the transfer of jet engine production from the failing Rover Company to Rolls-Royce, a pivotal decision that saved the entire Meteor program from collapse. Air Chief Marshal Sir Charles Portal served as Chief of the Air Staff, the RAF's highest uniformed post, from October 1940 until December 1945. He oversaw the strategic bombing campaign, the air defence of Britain, and the tactical air support that made the Normandy invasion possible. He was succeeded by Marshal of the RAF Lord Tedder in January 1946. Sir Stafford Cripps served as Minister of Aircraft Production from November 1942 to May 1945, maintaining aircraft production at over 2,000 units per month while setting realistic forecasts that allowed accurate planning. After the war, Cripps became Chancellor of the Exchequer in the Attlee government, where he implemented the austerity measures that shaped post-war Britain. After Labour's landslide election victory in July 1945, the Attlee government inherited a nation that was effectively bankrupt. Britain had borrowed massively to finance the war effort. Lend-Lease from the United States ended abruptly in August 1945. Defence spending had consumed over 52% of gross domestic product at its wartime peak. This would collapse to approximately 6% by 1950 as the government redirected resources to domestic priorities. Viscount Stansgate served as Secretary of State for Air from August 1945 to October 1946, overseeing the critical transition period when decisions about jet versus piston production were finalised. The Ministry of Aircraft Production itself was dissolved on April 1, 1946, absorbed into the Ministry of Supply. Britain's wartime aircraft industry, which had employed nearly 2 million workers and produced over 2,000 aircraft per month at its peak, collapsed rapidly after victory over Japan. Workers were demobilized. Factories were converted to civilian production. The industrial base that could have produced MB.5s or Spitefuls in quantity simply ceased to exist. In this environment of austerity and transition, the decision to concentrate remaining resources on jet aircraft was not irrational. The physics of propeller-driven flight imposed absolute limits that no amount of engineering brilliance could overcome. Propeller efficiency dropped sharply as blade tips approached the speed of sound. No piston fighter could ever fly much faster than 500 miles per hour, regardless of engine power or aerodynamic refinement. Jets had no such theoretical limit. The mistake was not in choosing jets. The mistake was in assuming the transition would be instant, that piston fighters could be discarded immediately, that the jets of 1945 would be ready to perform every mission that might be required of them. The decision-makers were betting on potential rather than demonstrated capability. They were right about the long-term direction of aviation technology. They were dangerously wrong about the timing. The Korean War proved how wrong that assumption was. On June 25, 1950, North Korean forces crossed the 38th parallel and invaded South Korea in a surprise attack that caught the Western powers completely unprepared. The conflict that followed over the next 3 years would expose every gap in the all-jet air force that planners had imagined. Early jet fighters suffered from fundamental operational limitations that their designers were still working to overcome. Their engines consumed fuel at prodigious rates, limiting combat radius and time on station. A Meteor F-3 could barely manage 500 miles on internal fuel, roughly half the range of a well-configured Mustang. Their thrust response was sluggish compared to piston engines, with several seconds of lag between throttle movement and power change, making them less maneuverable at low speeds and altitudes where most ground support missions were flown. Pilots accustomed to the instant response of piston engines found themselves constantly behind the aircraft's energy state. Early jet engines were also far less reliable than mature piston designs. Turbine blades could fail catastrophically with little warning. Compressor stalls during aggressive maneuvering could cause flameouts that might or might not relight. The maintenance burden was enormous, with engine overhaul intervals measured in tens of hours, rather than the hundreds of hours that late-war piston engines could achieve. The jets required long concrete runways for safe operation, runways that were scarce in the war-torn Korean peninsula. A Meteor needed at least 3,000 feet of hard surface to operate safely. A Mustang could use a dirt strip half that length. In the fluid early weeks of the war, when United Nations forces were pushed into the Pusan perimeter and every available aircraft was desperately needed, the jets could not operate from the forward fields where their presence was most needed. The United States Air Force was forced to make an embarrassing reversal. Units that had converted to the F-80C Shooting Star jet fighter were converted back to the F-51D Mustang, an aircraft that had first flown in 1940 and was considered obsolete by post-war planners. The Mustang could operate from rough forward airstrips that would destroy a jet's turbine engines with debris ingestion. It could loiter over front lines for hours while jets had perhaps 20 minutes of combat fuel. It could carry heavy bomb loads and rockets for ground attack. It could absorb battle damage and keep flying in ways that early jets with their vulnerable engines could not. Ground fire proved the deadliest threat to aircraft in Korea. Communist forces equipped their forward positions with heavy concentrations of anti-aircraft weapons, everything from rifle fire to heavy machine guns to radar-directed flak. Aircraft flying close air support missions had to descend into this maelstrom of fire to deliver their ordnance accurately. The liquid-cooled Merlin engine in the F-51D Mustang was vulnerable to this threat. A single bullet through the coolant system would cause the engine to overheat and seize within minutes. Mustang losses to ground fire mounted steadily throughout the conflict. The air-cooled radial-engined aircraft, like the F-4U Corsair and the AD Skyraider, proved far more survivable. A radial engine could absorb multiple bullet strikes and continue running. Individual cylinders could be damaged or destroyed without causing total engine failure. The United States Air Force's decision to scrap its P-47 Thunderbolt fleet after the war, replacing the rugged radial-engined fighter with the sleeker but more vulnerable Mustang, was bitterly criticized by pilots who watched their comrades go down from single bullet strikes. The F-82 Twin Mustang, America's last production piston fighter, vindicated itself spectacularly. On June 27, 1950, just 2 days after the invasion began, F-82 pilots scored the first US air-to-air kills of the war, shooting down North Korean aircraft near Gimpo Airfield. The Twin Mustang continued serving in Korea until its retirement on November 12, 1953, months after the armistice was signed. Piston-engined F-4U Corsairs, AD Skyraiders, and F-51 Mustangs bore the brunt of close air support operations throughout the conflict. The Royal Navy's decision to retain the Hawker Sea Fury rather than transition entirely to jets was vindicated in one of the most famous aerial engagements of the war. On August 9, 1952, 4 Sea Furies of 802, Naval Air Squadron from HMS Ocean were on a ground attack mission between Chinampo and Pyongyang when they were bounced by 8 MiG-15 jet fighters. The MiG-15 was vastly superior to the Sea Fury in speed and climb performance. It could reach 670 miles per hour, nearly 200 miles per hour faster than the piston fighter. It could climb to 40,000 feet where the Sea Fury could barely operate. On paper, the 4 Fleet Air Arm pilots faced certain destruction. What happened instead became legend. The Sea Furies, unable to run from the jets, turned into the attack and used their superior low-speed maneuverability to survive. At low altitude, where the MiG-15 pilots had to worry about stalling their swept-wing aircraft in tight turns, the Sea Fury's superior low-speed handling became an asset. One MiG-15 was shot down during the engagement. For many years, Lieutenant Peter Carmichael received credit for the kill and was awarded the Distinguished Service Cross. However, subsequent analysis of ammunition expenditure and squadron testimony led to the credit being officially reattributed in 2017 to Sub-Lieutenant Brian Ellis. Ellis had expended virtually all of his ammunition during the engagement, while Carmichael returned to the carrier with approximately 90% of his rounds unfired. Regardless of who fired the fatal shots, the engagement demonstrated that piston fighters retained tactical value even against swept-wing jets under the right circumstances. All 4 Sea Furies returned safely to their carrier. As veterans of the engagement later recalled, a jet simply could not dogfight a Sea Fury at low altitude. The Soviets had notably continued developing piston fighters longer than the Western powers. The Lavochkin LA-9 entered production in August 1946. The LA-11 long-range escort variant was produced through 1951, with over 1,000 aircraft built. Both types saw combat in Korea with Chinese and North Korean forces. On November 30, 1951, 16 LA-11s, escorting 9 Tupolev Tu, 2 bombers were ambushed by F-86 Sabres near the Yalu River, suffering heavy losses that effectively marked the end of the piston fighters' viability against modern swept-wing jets in the air superiority role. But until that moment, the Soviet hedging strategy had proven pragmatic. They kept piston fighters operational alongside their developing jet force, using them for missions suited to their characteristics, while reserving jets for situations requiring their superior performance. This approach, maintaining 2 to 3 years of overlap between the end of piston production and the full maturity of jet replacements, was exactly what British planners had failed to do. The MB.5 and the Spiteful would never have competed with MiG-15s for air superiority. By 1950, no piston fighter could survive against a modern swept-wing jet in pure air combat. But Korea was not fought in pure air combat. It was fought in mud and mountains, over rice paddies and ridgelines, where aircraft needed to loiter for hours, carry heavy ordnance loads, absorb ground fire and keep flying, operate from rough forward airstrips without long concrete runways. Every capability that piston fighters provided and early jets lacked was desperately needed in Korea. The characteristics that the MB.5 represented, its exceptional handling qualities, its superb maintainability that allowed rapid turnaround, its long range on internal fuel, would have been exactly what Korea demanded. The aircraft that the Air Ministry dismissed as obsolete in 1944 would have been desperately useful in 1950. James Martin never saw his fighter enter squadron service, but his response to Valentine Baker's death transformed aviation safety in ways that continue saving lives today. On July 24, 1946, Bernard Lynch became the first person to eject from an aircraft in mid-flight outside Germany, blasting clear of a specially modified Gloster Meteor at 320 miles per hour and 8,000 feet over Chalgrove Airfield in Oxfordshire. Lynch descended safely by parachute and walked away from the experience, proving that the Martin-Baker ejection seat could save a pilot's life when all else failed. Martin devoted the rest of his career to perfecting ejection seat technology. The company he founded became the world's leading manufacturer of ejection seats, equipping combat aircraft in 93 air forces around the world. As of December 2025, Martin-Baker ejection seats have saved approximately 7,812 lives, a number that grows every year as pilots escape from stricken aircraft using Martin's invention. James Martin received the Order of the British Empire in 1950, was made Commander of the Order of the British Empire in 1957, and was knighted in 1965 for his contributions to aviation safety. He died on January 5, 1981, at the age of 87. His legacy is measured not in aircraft that flew combat missions, but in pilots who survived to fly again. The sole MB.5 prototype passed through various hands after testing ended. It was loaned to de Havilland for propeller testing in late 1947. Captain Eric Brown flew it at RAF Farnborough in 1948 during evaluation trials. Then, on May 5, 1948, the aircraft was sent to RAF Wattisham as a ground training airframe, its flying days over. It was later moved to RAF Bircham Newton, where it served as a ground target for weapons training. The aircraft was reportedly burned around 1963, an inglorious end for a machine that every pilot who flew it called extraordinary. Those pilot assessments deserve to be remembered. Captain Eric Brown flew 487 aircraft types during his career, more than any pilot in history, a Guinness World Record that stands unchallenged. After flying the MB.5, Brown wrote that in his opinion this was an outstanding aircraft, particularly when regarded in the light of the fact that it made its maiden flight as early as May 1944. He added that he had never felt more comfortable in a new aircraft. Squadron leader Janusz Zurakowski, the distinguished Polish fighter pilot who had fought in the Battle of Britain and later became famous for his aerobatic displays, flew the MB.5 at the Farnborough Air Show in June 1946. He declared it the best airplane he had ever flown, better in many ways than the Spitfire. He questioned publicly why such an aircraft had never entered service. Air Vice Marshal John Boothman flew the MB.5 at Boscombe Down on April 17, 1946, and reported that it was quite an outstanding aircraft, insofar as control and stability were concerned. He said he had seldom flown an aircraft which combined the positive stability of the American fighter with the extreme maneuverability usually associated with British designs. The official evaluation from the Aeroplane and Armament Experimental Establishment stated that the general design and layout of the Martin-Baker MB.5 was excellent and was definitely better, from the engineering and maintenance aspect, than any other similar type of aircraft. The layout of the cockpit might very well be made a standard for normal piston-engined fighters. These were the most experienced test pilots and official evaluators in Britain, delivering unanimous praise for an aircraft that the Air Ministry had already decided to abandon before any of them flew it. The lessons of this story extend far beyond aviation history. Technological transitions rarely happen as cleanly as planners expect. The men who cancelled Britain's advanced piston fighters believed they were making a clear choice between past and future. In reality, they were making a bet about timing, a bet about how quickly jets would mature and how soon piston fighters would become irrelevant. They lost that bet by approximately 5 years, 5 years during which a conflict erupted that demanded exactly the capabilities they had discarded. Institutional momentum can override evidence. By the time the MB.5 had resolved its early problems and begun demonstrating its true potential, the decision to cancel had already been made. The bureaucratic machinery had moved on, the funding had been redirected, the future had been decided, and the MB.5 was not part of it. Excellence alone is never enough. James Martin built what multiple experts called the finest piston fighter ever designed. It did not matter. The decision-makers were not looking for the best piston fighter. They were looking for the future, and they had decided the future did not include propellers. Assumptions about warfare can be dangerously wrong. The planners who cancelled piston fighters assumed future wars would be fought at high speed and high altitude, where jets held absolute advantage. Korea was fought at low altitude and moderate speed, where the attributes that piston fighters possessed mattered enormously. Britain's finest piston fighters were cancelled, not because they were inadequate, but because the future arrived unevenly, and the men who made the decisions could not imagine that the present would still matter. If you found this story as compelling as we did, please take a moment to like this video. It helps us share more forgotten stories from aviation history. Subscribe to stay connected with these untold accounts. Each one matters. Each one deserves to be remembered. And we would love to hear from you. Leave a comment below telling us where you are watching from. Our community spans the globe, from aviation enthusiasts to history scholars. You are part of something special here. Thank you for watching, and thank you for keeping these stories alive.